All right, so we're going to go over typical operating conditions of an air conditioner. So this covers, the temperatures at which it should run, inside and outside, and then how the system should perform. Obviously, we're going to hit this quickly, and we will go over this more in class. So your design conditions for air conditioning, and obviously we're probably not going to be running at these if things are running right. 80-degree inside air temperature, 95-degree outside air temperature, 50% humidity. These are rated. Standard efficiency systems, um, this is where they're going to be, any system. This is where they're going to be sized. This is how they're going to perform at these conditions. So hopefully we're not running an 80-degree inside air temperature. That's the biggest difference from design versus reality, but just want you to know that that's kind of what they're based on. So when they say they're getting 36,000 BTUs or whatever, this is what they're doing it on. Standard efficiency systems condense at about 125 degrees at design conditions. So we're going to get a couple of rules, kind of rough rules, I guess you'd say, rules of thumb that we'll go by. And one of those is how much warmer does the condenser temperature need to be than the outside air, and the other is how much cooler does your evaporator need to be than the inside air. Another thing that you need to remember is that that air conditioning system's job is not only to remove heat, but also to remove moisture. So moisture levels will increase or decrease the system's performance based on how much moisture is present. So if you have a lot of humidity, then the temperature performance may not be as good as you would expect. All right, so you need to understand that the relationship between pressures and temperatures, as the temperature around something increases or decreases, the pressure of the refrigerant inside of that system goes along with it. So just think about if you took a jug of 410A refrigerant and it was sitting in a room that was 70 degrees, and after a few minutes of sitting in there, it should go to standing pressure on your PT chart of whatever temperature it is, pressure it is at that temperature. If you took that same jug of refrigerant and you put it outside in the sunlight, 90 degrees, it's going to go to whatever pressure it should go to at 90. So your system is no different. Your system has running pressures and it has standing pressure. So standing pressure is when the system's off, when there's nothing, the compressor's not running, there's no low side, high side, it's just basically a container of refrigerant. So if you go up to a system and it's not running, you put your gauges on it, they should go to standing pressure of whatever temperature it is outside. That can vary a little bit, but if it's a 90-degree day, it should go to a 90-degree saturation temp and whatever pressure that is. So now when you start your system, you create low side and high side pressures. And so when you lower the pressure on the low side, your temperature is going to go down as well. Well, why do we do that? To make the system pick up heat, we have to move from hot to cold. And so we have to make that evaporator coil colder than whatever it is that it's removing the heat from. So if this is a house, then if it's 70 degrees in the house, we have to make it colder. We also know that refrigerant has to be evaporating, but for just in terms of temperature, it has to be colder. So hot goes to cold, heat in the house attracts to the colder coil, and on the high side, once we pick that heat up, we run it through the compressor, we raise its pressure. The reason we raise its pressure is to raise its temperature. If we raise its temperature, the pressure goes with it. The system gets warmer on the condensing side, on the high side, and it rejects the heat. So it has to be warmer than the air outside to reject the heat. So just again, inside coil, evaporator, has to be colder than the inside air. Outside coil, condenser, has to be, let me say that again, make sure I said that right. Indoor coil has to be colder than the inside air, the air that it's picking up heat from. So the evaporator must be colder than the room temperature or the return temperature. The outside coil, the condenser, has to be warmer than the temperature of the air outside or the ambient outside. So if it's 95 outside, it has to be warmer. How much warmer? Well, that's where it goes back to this. So if it's a 95-degree day, standard efficiency systems are usually going to run 20 to 30 degrees above ambient. So we get this rule that you're going to hear me say a lot. And you can write this down. Indoor minus 30, outdoor plus 20. That's a very general rule. It's not the be all end all, but it does get you in the ballpark. And so what it says is, and sometimes you'll see it indoor minus 35. But what that's saying is at a 75 degree indoor temperature, for example, you'd have to have a 30 to 35 degree colder indoor coil. So that's a 40 to 45 degree coil. That's where it's usually going to run to pick up the right amount of heat. Same thing on the high side. It's outdoor plus 20, which means if it's 95 outside, you're going to be running 115. Now, efficiency can greatly affect the performance of the high side. So the more efficient a system is, the lower that number will be. A higher efficiency system will run at maybe 15 degrees over ambient instead of 20, 25, or 30. An old system that's 25 years old and it's got a small condenser on it, it may run at 30 to 35 over ambient because it's less efficient at removing that heat. So it has to raise the pressure higher so that it gets rid of it. That's where some of your efficiency comes from. Is newer systems will use larger coils, which allows it to run and move the same amount of heat over a greater surface area, which keeps its pressure down, which keeps the pressure on the compressor down, which keeps the amperage down, which reduces your electrical usage. So in a nutshell, that's one reason why some of the more efficient systems have huge oversized coils, so they can move it easier without raising the pressure so high. Because we know that hot goes to cold at a rate relative to the delta T, or the temperature difference. So the higher the temperature difference, the faster that heat's going to leave. But in order to get that heat up to that temperature, we have to raise the pressure higher, which puts more work on the compressor. So just it all ties together. So your evaporator, a good baseline, if it's 75 degrees in the house, is a 40 degree coil. That's with 50% humidity, and your approximate superheat is 10 degrees. So if you were just to put a blanket over it and say, if everything inside is normal, normal air temps, what should I see? I'm looking for about a 40 degree coil and 8 to 12 degrees of superheat. Now, there are some things that can change that, but just normally, that's a really good guideline. So I would snap a picture of that slide right there. That's a good guideline. That'll get you started. If you've got a 70 to 75 degree house, and you've got a 40 degree evaporator, 40 degree vapor saturation temperature on your gauges, that's good. Now, when I say coil temp or evaporator temp, I'm not meaning that you're measuring it with a thermometer. I'm meaning the vapor saturation temperature inside the coil, the refrigerant temperature. That's what we're calling the coil temp. Now, you also have superheat on that as well. So that 10 degrees of superheat, if you're looking at this picture here, that refrigerant's working its way through the coil, and as it goes, it's picking up heat, causing it to boil. And once it becomes 100% vapor, it reaches saturation where it can no longer evaporate. Now it is sensibly changing. So 10 degrees of superheat, hopefully we know this, is additional heat that's added to that line in addition to the saturation temp. So a system that's running at 40 degrees vapor saturation and a 10 degree superheat will have a suction line of 50 degrees. If you need to rewind that, go back and hear that again, that's fine. But just want to make sure you understand that. I'm going through this quick, just kind of hitting the high points. All right, if I increase load, so we know normal, if we say that's normal, 40 degree coil at, a 70 to 75 degree house. Now, what if all of a sudden we increase the temperature inside of the house? Okay, so if we just say we want a 40 degree coil, there's times to where 40 degrees may not be enough, or it may be too much. So that's where it's better to think in terms of temperature difference. That difference between that 30 to 35 difference, that's what you're going to call your TD, your temperature difference. We go by that more than just a standard 40 degrees, because what if it's 80, 85 in the house? Maybe it's been off all day, you haven't been able to work on it, and you get there, you get it running, and you're trying to figure out where your gauges should go, If you shoot for a 40-degree coil, you're going to be undercharged. If you go by the indoor minus 30 to 35, if you know it's 80 degrees in the house, now you're looking for a 45 to 50 degree saturation temp. But as it cools down in the house, that temperature and pressure should come with it. So it should come back to normal without having to sit there and wait for it to be normal. So you don't have to have the system running at ideal temperatures to predict what it's going to do, as long as you're factoring in that it's hotter than normal in the house. Okay, so I'm skimming through this pretty quick. Your limitations on your system, usually outdoor temperatures of about 50 degrees, 55 is about as low as you're ever going to want to run an air conditioner. If you're testing one, you put one in the winter, it's going to recommend, if it's below 55, that you come back and that you charge it up properly. Check it all in the spring. When it's above 70 would be probably ideal. There are ways around that, but that's just kind of a good guideline. All right. So higher efficiency systems, and I'm going to say what they're calling standard is like probably 10 SEER, 11 SEER stuff, old stuff. High efficiency at this point, probably when this slide was made, was 20, 25 above, and now some of this high efficiency stuff is probably only running 15 above outdoor ambient. Always, if you've got information with the system, if they're saying, it needs to be at a such and such subcooling or whatever, keep that in mind. Another thing, the superheat rating, if you have a TXV, you're going to look at superheat, but you're going to go by subcooling, because the job of the TXV is to maintain a constant superheat. So all the information is going to come into play. Delta, your vapor saturation, your liquid saturation, temperature differences between indoor and outdoor. So you're factoring everything in. So there's no just take a reading and you're good. Like, you're going to factor it all in to make sure that everything's running as it should. All right, so like I said, I'm skimming through this pretty quickly, but you can hear my kid in the other room. SEER, EER and SEER. So SEER and EER. EER is the energy efficiency ratio, which is a number that a lot of the units are going to have on there. It's found by taking the BTU output over the wattage input. Larger the number, the more efficient the system. SEER is what people are probably more familiar with, and it's similar. It's just a little different. It factors in seasonal changes. The higher the number, the better the equipment. So same thing. And just kind of, this is looking at electricals. We're not going to spend a lot of time on that, but okay. So if I was going to summarize this, I would say that you need to remember indoor minus 30 to 35, outdoor plus 20. Normal operating conditions, it's warm outside, warm enough to run an air conditioner, and it's 75 degrees in the house or so. You're looking at a 40-degree evaporator temperature, 10 degrees for superheat. Now, if it's a fixed piston, that number could change a little bit, but ideally we're looking for 10 degrees at operating condition, normal conditions. Outdoor temperature, 20 degrees, 15 to 30 degrees warmer than outside, depending on the efficiency of the system. So a standard efficiency 14 SEER system is probably going to run in that 20 degrees over ambient. If it's 90 degrees outside, 110 degree temperature on the high side. 75 in the house, 40 to 45 degree coil on the low side. So that gets you in the ballpark, and then from there you can kind of tweak stuff and make sure. So I always start with pressures, temperatures to make sure that I'm close, because I've seen people that start with superheat subcooling, but their pressures, temperatures are way out of whack. You can't really, you're using those initial temperature readings and pressure readings to make sure that you're close, and then you use superheat subcooling to determine the tweaks, the fine line, between overcharge, undercharge, overfeeding, starved, and all that stuff. So don't start with superheat subcooling. Start with your pressures, your temperatures.